We humans have explored so much. We've climbed the highest mountains, we've sailed across vast oceans, we've even ventured into the vacuum of space. But there's one frontier that remains truly uncharted: time. It's the most familiar of mysteries. We experience it every single day. Yet time remains one of the biggest enigmas in the universe. What is time, really? Where does it go? Can we control it? These are questions that have puzzled philosophers and scientists for centuries. Time is the silent conductor of the universe's grand symphony. It dictates the rhythm of our lives, from the beating of our hearts to the rise and fall of civilizations. But grasp it we cannot. Time, like a river, seems to flow inexorably forward. But is that always the case? Einstein, with his revolutionary theories, showed us that time is far more slippery and elusive than we ever imagined. It can bend, it can stretch, and it might even loop back on itself. Think about it. Every moment that has ever been still exists somewhere in the fabric of space-time. The Big Bang, the extinction of the dinosaurs, your first kiss, they're all out there, frozen in the vast cosmic timeline. The past isn't gone. It's just as real and present as the here and now. And the future, well, that's already unfolding somewhere out there in the vast tapestry of space-time. So buckle up. We're about to embark on a mind-bending journey through the cosmos, exploring the mysteries of time itself. Get ready to have your preconceived notions challenged as we delve into the heart of this ultimate enigma. We measure time in seconds, minutes, hours. It's the steady beat that governs our daily routines. We set our alarms, schedule meetings, and celebrate anniversaries, all in accordance with time's relentless march. But have you ever stopped to think about what we're really measuring? What is this invisible force that dictates our lives? And on a basic level, we experience time as a linear progression from past to present to future. It seems straightforward. But as Einstein taught us, time is relative. What does that even mean? Well, imagine two identical clocks. One stays here on Earth, the other goes on a high-speed rocket trip through space. When the rocket returns, its clock will have ticked slightly slower than the Earth-bound one. This is time dilation, and it's one of the mind-bending consequences of Einstein's theories. Time, it turns out, is not absolute. It's influenced by gravity and speed. The stronger the gravitational field, the slower time runs. The faster you move, the slower time ticks for you relative to someone standing still. These effects are usually minuscule in our everyday lives, but they become significant at speeds approaching the speed of light or near extremely massive objects like black holes. So the next time you glance at your watch, remember that you're not just looking at a device for measuring seconds and minutes. You're looking at a window into the very fabric of the universe, a fabric that's far more strange and wonderful than we could have ever imagined. Albert Einstein, the most famous scientist of all time, revolutionized our understanding of time. His theory of special relativity, published in 1905, shattered the Newtonian idea of absolute time. Time, Einstein demonstrated, is relative. It's intertwined with space to form a four-dimensional fabric called space-time. Imagine space-time as a giant trampoline. A massive object like the sun creates a dip in this fabric, a gravitational well. This warping of space-time is what we experience as gravity. It's not just that massive objects attract each other, they actually distort the very fabric of time and space around them. But Einstein didn't stop there. His theory of general relativity, published in 1915, went even further, predicting the existence of mind-boggling phenomena like black holes and wormholes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They're like cosmic vacuum cleaners, sucking in anything that gets too close. Wormholes, on the other hand, are hypothetical tunnels through space-time, connecting distant points in the universe. Imagine folding a piece of paper in half and poking a hole through it. That's a simplified way to visualize a wormhole. It's a shortcut through the fabric of space-time, potentially allowing us to travel vast cosmic distances in the blink of an eye. Einstein's theories have been tested and confirmed countless times, and they've opened up a Pandora's box of possibilities. They've given us the tools to explore the universe in ways we never thought possible. Time travel, it's the stuff of countless science fiction novels and movies, but could it actually be possible? According to Einstein's theories, the answer might be a cautious maybe. You see, time travel to the future is definitely on the table. Remember time dilation? The faster you travel, the slower time goes for you relative to someone back on Earth. Imagine boarding a spaceship that could travel at a significant percentage of the speed of light. You embark on a round trip to a distant star system. When you return to Earth, years, decades, or even centuries could have passed, depending on how close to the speed of light you traveled. You would have effectively traveled into the future. Traveling to the past, however, is a much trickier proposition. It would involve bending space-time to such an extreme that it loops back on itself, creating what's known as a closed time-like curve. While this doesn't violate any known laws of physics, the practical challenges and paradoxes it presents are enormous. Imagine, for example, traveling back in time and accidentally preventing your own birth. It's the classic grandfather paradox. These paradoxes suggest that there might be some fundamental laws of physics yet to be discovered that prevent time travel to the past. Section 5. The mystery of time's arrow. We experience time as an arrow flying unerringly in one direction forward, from the past through the present and into the future. But why is this so? Why does time seem to have a preferred direction? This is the mystery of time's arrow, and it's a puzzle that continues to baffle physicists. In the grand scheme of the universe, most physical laws are time-symmetrical. That means they would work just as well if time ran in reverse. Think about a game of billiards. If you filmed the balls colliding and then played the film backward, it would look perfectly normal. You wouldn't be able to tell that time was running in reverse. However, there's one crucial exception, the second law of thermodynamics. This law states that entropy, a measure of disorder or randomness, always increases over time in a closed system. Imagine a glass of water shattering on the floor. It's easy to imagine this happening forward in time, but you'd never see shards of glass spontaneously assembling themselves into a pristine glass, would you? This tendency for entropy to increase seems to be the driving force behind time's arrow. It's what gives time its directionality from a more ordered past to a more disordered future. But why entropy increases in the first place remains one of the biggest unsolved mysteries in physics. Section 6. Time dilation. Time flies when you're having fun, literally. Remember that thought experiment with the two clocks. One stays on Earth and the other takes a high-speed trip through space. When the spacefaring clock returns, it's lagging behind its Earth-bound counterpart. This is time dilation in action. And it's not just a theoretical concept. It's been experimentally verified numerous times. In fact, time dilation affects our everyday lives, even if we don't realize it. GPS satellites, for example, have to account for time dilation. They orbit Earth at high speeds, so their clocks run slightly slower than clocks on the ground. If they didn't make adjustments for this difference, GPS navigation systems would be wildly inaccurate. Time dilation isn't just a quirk of Einstein's theories. It's a fundamental aspect of the universe we live in. It tells us that time is not the rigid, unchanging entity we once thought it was. It's fluid, malleable, and inextricably linked to gravity and motion. So the next time someone tells you time flies when you're having fun, you can tell them it's not just a saying. It's a fundamental principle of the cosmos. Section 7. The quantum realm. Time gets even weirder. If you thought Einstein's theories were mind-bending, just wait until you delve into the bizarre world of quantum mechanics. In the quantum realm, the subatomic world of particles and energy, the rules of classical physics break down. And time, well, time gets even weirder. One of the most bizarre aspects of quantum mechanics is the idea of superposition. In the quantum world, particles don't exist in a definite state until they're observed. Instead, they exist in a superposition of all possible states simultaneously. Imagine a coin spinning in the air. Until it lands, it's both heads and tails at the same time. That's superposition. Now, apply this concept to time. What if, at the quantum level, time itself exists in a superposition of states? What if the past, present, and future are all happening at once in some strange, probabilistic way? This is the mind-boggling realm of quantum time, where our everyday intuitions about cause and effect go out the window. Some physicists believe that a deeper understanding of quantum mechanics might hold the key to unlocking the secrets of time travel, or even manipulating time itself. It's a realm of science that's still shrouded in mystery, but one thing's for sure, it promises to rewrite everything we thought we knew about time. Section 8. Time, the ultimate frontier. We've journeyed from the familiar tick-tock of our clocks to the mind-bending realm of quantum time. We've explored Einstein's revolutionary theories and pondered the possibility of time travel. But one thing remains clear: time is the ultimate frontier. It's the invisible hand that shapes our lives, the universe's grand orchestrator. It's a mystery that has captivated humanity for millennia, and it's a challenge that continues to inspire scientists and dreamers alike. We've only just begun to scratch the surface of understanding this enigmatic force. There are still so many unanswered questions. Can we control time? Can we reverse it? Is time travel truly possible? These are questions that will continue to drive scientific inquiry for generations to come. Section 9. Keep exploring. The journey through time continues. As we've seen, time is not just a measure, it's a fundamental aspect of the universe, woven into the very fabric of reality. It's a river that carries us along, but it's also a vast ocean waiting to be explored. So I encourage you, keep questioning, keep exploring, and keep looking up at the stars. The universe is full of wonders, and the journey through time is just beginning. Read books, watch documentaries, and engage in conversations about these mind-blowing concepts. The more you learn, the more you'll realize how much more there is to discover. Who knows what breakthroughs await us in the future? Perhaps one day we'll unlock the secrets of time itself. Until then, keep exploring the cosmos.